Testing, testing. 1, 2, 3. Testing, testing. Picture. That'll do. Hello, everyone. Welcome to yet another edition of How Will the Universe Conspire Against the Lecture Today, featuring your favorite online professor, Mr. Nicholas Moore. Yes. Anyway, I see I've only got 16 people. Oh, wait, I've got 28 people concurrently watching, so awesome. That's 1/3 what it usually is, so hopefully as time goes on, we get a few more people clicking through. I don't know, maybe everybody has assignment fatigue from the assignment that's due this evening and the test that was due over the weekend, all the rest of that sort of thing. At any rate, oh, I usually watch chat on my phone. Just remembered. Should probably do that. So, boy, the weather has been nice, eh? It's bloody marvelous. I don't know, though. It's getting a little too hot, I think. But, you know. That's the funny thing. It goes from, like, too cold to, like, more than way too hot in the space of, like, 3 days, and it's going to be like this for the rest of the summer. It's ridiculous. No, Khan Academy is pretty helpful. That's true. So, we are going to be talking today about a more technical subject. This one is called Numerical Computations. We are going to be talking about such things as how the computer represents the numbers underlying everything we do. So, if you're already familiar with the binary system, some of this is going to be a review, but that's okay. Review is good. Oh, yeah. So that actually probably bears some mention. If any of you have not received the email at this point, which I imagine probably most of you have, but, you know, at any rate, the university had a statement today that all of the classes for the fall semester are going to be moved online. That is I imagine that this decision was made on the part of university administration with, like, a great deal of deliberation. Like, I'm sure nobody wanted this, but, you know, if you listen to what the current projections are for either I leave and lose a house for a winter or pay for 4 useless months. Oosh. Ooch. Yeah. Gross. My sympathies, Ryan. Like, from some of the projections that I've seen, the sort of peak of the second wave will be sometime late August, early September. So it makes a lot of sense why the university would make this decision. It doesn't make it any easier. I'm just glad I'm not a chemistry prof. Can you imagine? Like sending everybody their chemicals to experiment with by mail? That just wouldn't work at all. It's like, okay, here you go. Here's all the ammonium nitrate that we're using for lab number 6. And then the government's like, wait, you're not allowed to ship that stuff. Yeah. Oh, yeah, and good luck if you're trying to find work, really. Like, yeesh. Yeah, it's not great. I don't know. Maybe the government will be able to pay everybody for everything all the way through to September, but, I mean, my God, like, the problem is that, you know, in pragmatic terms, the like, the country's got to run out of money for this at some point, right? But I don't know. I'm just a humble professor. Those sorts of things, they're not really important. But to me, they're certainly important. But you know, my God, yeah. No. So, oh yeah, I sometimes forget that I like to make the occasional joke about chemists, and there are also chemists in the crowd. But oh my goodness. Just so you know, I don't actually hate chemists or dislike chemists or anything like that. Actually, if I hadn't gone into computers, I probably would have gone into chemistry. But yeah, yeah, that's the other. Yeah. Oh my goodness. Well, let's just try to learn some code stuff and see how it goes, eh? Maybe everything will be online, like they'll just upload us to the matrix, and then if you can program, then you have the literal power of a god. But anyway, so we're going to talk about numbers. We're going to talk about integers. We're going to talk about reals and fractionals. We're going to talk about approximation algorithms, and we're going to have some cautionary tales about using floating point representation. Ooh, I have been asked, don't I have a PhD defense coming up or something? Yeah, hopefully sometime this century. Um, um, yeah. That is the sort of thing that they can actually have remotely. They have been doing, like, with respect to graduate studies, they've been continuing doing all of the defenses and the department, like, when you're a grad student, you have to do an annual meeting with a supervisory committee, which is a committee of 3 professors, roughly, who just make sure that you're still on track to graduate, because that's a thing that you can slip away from as time goes on. But with respect to defenses and all that sort of thing, things are technically still supposed to be going on as usual. A lot of the in our department, like, all you really need for your research is a computer, and sometimes a fancy one depending on what you do. But the nice thing about fancy computers is that you can often log into them remotely and just do your stuff that way. So with respect to, as you might expect, computer science majors are minimally impacted by the fact that they don't need to physically exist anymore. But you know, then again, you know, there's all the psychological issues with respect to being stuck in a house all the time. So, you know, I know that personally, my productivity has not been, like, I'm getting back up to it, but for the first few weeks, it was pretty bad. Just because it was like, wow, the world is ending. What's the point of anything? But anyway, turns out the world hasn't ended yet. So anyway, let's talk about integers. So the thing that you have to understand in order to get binary is that you are operating in a different base system. If you think about the way that numbers work, like Arabic numerals, yeah. I agree with some of what Chad has said. So if you think about how an Arabic numeral works, it's on a base 10 system, right? And one of the big innovations with numbers was 0 as a placeholder, actually. So the Roman numeral system, for example, didn't have 0. But what you have is you have multiples of whatever the base of the number system is, and you multiply whatever the number is in that place value by whatever power of the base number in order to get the contribution of that digit to the value of the number, so to speak. So in the decimal system, the number 2053 is a 2, a 0, a 5, and a 3. 2 times 10 to the third, 0 times 2 times 10 to the second, 5 times 10 to the first, and 3 times 10 to the 0th. So even when you're just multiplying by 1, that's still a power of the base of the number system. So this is fine. In the decimal system best base system, in the decimal system, it's the exact same thing, except the only digits which are allowable are 1s and 0s. So in this particular case, 1101, we have 1 times 2 to the third, plus 1 times 2 to the second, plus 0 times 2 to the first, plus 1 times 2 to the 0th, which is 8 plus 4 plus 1, which is 13, which is a, that's how the binary system works. So there are some caveats with this. The representation of integers is basically just a straightforward implementation of this, at least with respect to positive integers. Once you start getting into negative integers, things get a little more complicated. There are basically two major schemes for that. One is to have an additional digit or an additional bit in the byte or word which represents the sign of the number. So if it's 0, it's positive. If it's 1, it's negative, or vice versa. And then you also have what's called 2's complement, which is something that I'm just saying so that you've heard the word before. It's not important for you to understand it at this level. But I just want to point out that this is what is referred to as big endian representation, because the end that you start with is the big one. It's interesting, actually. This is going to seem like an unrelated tangent, but it's actually quite related. I was reading a book for pleasure over the last couple of weeks. I've been reading Gulliver's Travels, which, if you've never heard of the book, it is 1700s British sort of satirical comedy travel story thing. If you know that story with the guy who arrives at an island, but he's a giant, and there are all these little people who tie him up and capture him, that's Gulliver's Travels. But anyway, in that story, you have the Lilliputians, who are the tiny people, and they have neighbors who are also tiny people. They're about yay big, and they are in an old war with the other people whose name I forget, and they are the Lilliputians, I believe, are the big Endians, and the other people are the little Endians. And within the context of the book, this means when you crack open an egg, do you start with the big end, or do you start with the little end? Are you big or little endian? And that, I believe, is the derivation of this term in computing. Yes, Gulliver's Travels has been adapted into movies many, many, many times over the years. At one point by Jack Black, which is less true to the original. But the original is like 300 years old, so whatever. But anyway, so if you can't remember big versus little endian, think about cracking an egg. Of course, you have to be right-handed. So if you're a left-handed person, yes, it's Bellafusidians or something like that. Thank you, Rob. Way to go, Rob. Anyway, so if you have trouble remembering which representation you're dealing with, first imagine yourself as a right-handed person if you're not a right-handed person, and then imagine yourself cracking open an egg Do you have the big? Are you cracking open the big end or the little end? And that'll give you big versus little endian. There you go. Anyway, so so here's a question. What is the base 10 representation of the following binary number? 0110111. Is it 1, 11, 2, 27, 3, 54, 4, 59, or 5? Why are you doing this quiz? You know that quizzes take too long in this format. Please enter your answers into chat now. Verticadians. Who cracks their eggs vertically? It's verticadians. Lefties, I agree that you have rights. Ha! Lefties have rights. Ah! I see what you did there. Lefties have rights. Anyway, we have a pretty consistent. Everybody says 27, so that would be 1 plus 2, skip the 4, plus 8, plus 16. So that's 24, plus 2 is 26, plus 1 is 27. There you go. So the answer is 2, 27. Bing! So we've got, so if we have binary and decimal numbers, it's useful to, oh, what about vegans? Vegans would be non-endians, I guess. Anti-endians. Anti-disestablishment endians. Anyway. So, when you have, now that we have binary as a thing that we know about, it's important to know how to convert between decimal numbers and binary numbers. So, of course, in order to compute the decimal number from the binary number, we do exactly the thing that we did. We just, you know, excuse me, count out the number that, vegetabilists, yes. You count out the number that each place value is worth, and then you add them all together. So this is a little bit tricky in Python because of the whole zero indexing thing, right? You don't like, if you're starting from the back and you're going forward, the index is actually equal to the number that you have here. But there are a number of ways that you can convert, which are going to be interesting. So let's write an algorithm to do this, because of course that's how we do things. So compute the sum of the relevant powers of 2. Boop-a-doop-doop-a-doop. Let's take a look. So, definition. What are we doing? Binary? Is it binary to decimal? Yes. Okay. So bin to dec. So, interesting thing, right? In some programming languages, you have dedicated data formats specifically for representing binary data. So in some languages, these are called bytes or bit vectors. It's actually extremely common in hardware programming. However, the way that Python represents numbers in any non-decimals format, actually, not just binary numbers, is as a string. So if you have some sequence of 1s and 0s, that is a binary number in Haskell, Python, pardon me. So in a lot of other languages, you will see binary literals written without the quotation marks, first of all, because they are not, like that. But you will also see them with this sort of 0B or sometimes with a apostrophe like that notation. These are how other languages will represent binary numbers ordinarily. No, X is for hexadecimal. So if we have this string representing a binary number, and incidentally, a string is like the least possible efficient way possible of representing a binary number. But anyway, it's quite simple. We establish some index which starts at 0, while actually we could start at -1, couldn't we? Could do that too. While j is less than the length of b, sum is equal to 0, sum is equal to plus equals b at I times j 2 to the j. Then I minus equals 1 and j plus equals 1. Return sum. So let's just do some easy ones to see if we get our algorithm correct. Yep, syntax error. I'm using these. That's a not Python thing to do. Type error. Let's convert it to an integer, shall we? Yes. Yeah, so there we go. Is this like a hybrid of Python and C? It's actually a hybrid of Python and literally every other language. Yes. Python is built on C, demonstrating its true inferiority. Real languages are built on the same language that they are. I'll just go out on a limb and say it. So anyway, we now have a functional algorithm which converts binary numbers to decimal numbers. There you go. Notice I've got two counters going here, right? I've got one counting up and one counting down. In theory, I could write some mathematical expression in here to, it would probably be the length of b minus 1 minus j or something like that, I think. And then we could get rid of I. Maybe that'll still work. It'll still work! There you go. Yeah. Yeah, so Python just takes the best from every other language. Some people call that stealing, but yeah, sure. I find myself rarely, if ever, using while loops. I mostly use for loops. Is this normal? It depends on the application. Generally speaking, I would say that I use one while loop for every 3 or 4 for loops that I use when I'm writing solutions to the test and stuff like that. Generally speaking, this is because a lot of the looping that you'll be doing is centered around the data structures. And these data structures are often iterable. The thing that I wanted to do with this particular example, however, I wanted to use a while loop because I wanted to demonstrate the numerical, the numeracy of the fact that the index and the exponent are related to each other, right? But anyway, that's sort of... Oh, we should test to see if this is little or big endian, shouldn't we? So, 15, yes, so that's big endian, because that is bigger. Interesting. Do I sound okay at 1.75? I don't know. That's interesting. I guess I'm kind of an old fuddy-duddy, but I've never really been into, I've never really thought to increase the playback speed. Could I please explain that code? Okay, I will explain that code. So, I will show you the correspondence with the slide. So you see this summation right here? When you see a summation in a formula and you're having to translate that formula into code, what you're doing is what you should do there is you should write a loop that performs the summation. That's what I'm doing here. You can see I've got the sum. I've got I guess if I wanted to do it correctly according to the slide, I would make this j into an I. But you can see that mathematically expressed, we're doing the sum from 0 to n minus 1, which is the length, right? So the summation notation includes the case where n minus 1 is done, but since the while loop will not include the case where I is equal to the length of b, this is actually going up to 1 less than the length of b, and of course the length of b in this case is n, right? So you've got n digits here. So this is corresponding here. Then we've got 2 to the power of 1 minus I times b to the I. Well, that's interesting. That's actually I did it the other way. I applied that to b, and you get the same result. I can even demonstrate that now. See? You get the same result. It's like going this way or going that way. It's the same thing. So the question is, couldn't we just use int to achieve this goal? Yes. So the purpose of this demonstration is to reveal how the binary system works, rather than to just give you all of the tools. Obviously, Python has built-in stuff to convert from a binary representation to a decimal representation. Obviously, right? The purpose here is to show you what the numerical relationship is. And, you're going to get a lot of that in this slide deck. So there you go. So, starting with the leftmost digit, the accumulator is multiplied by the base, and the next digit is added. So there's another way of going about this called Horner's rule. And rather than going through this summation style thing that you see here, you can also do it in this manner, where instead of multiplying by 10 to the power of 3, you multiply it by just 10, then you add the next digit and you multiply by 10, add the next digit, multiply by 10. Same as that idea, but as applied to binary, that is called Horner's rule, and we shall that's what you got right here. So basically the same thing, but slightly differently spoken. So converting from decimal to binary, that's a little bit more operationally intensive, shall we say. So if we are trying to convert a number from the decimal system into the binary system, the first thing that you have to do is you have to extract out what all of the digits are, right? It's a general process of extracting a digit and then dividing by the base of the value, right? So fortunately, we have modulo to assist us with this. So if we were to convert the number 13 in the decimal system into binary, the first thing we do is we take the modulo with 2. This will tell us what the least significant digit is. So because it doesn't matter what your number is, if it's even, then the first binary digit, or the least important binary digit, is going to be 0. Otherwise, it's going to be 1. Yeah. If there are any true mathematicians in the audience, I disavow me being considered a true mathematician. Anyway, so if you do that, and then you divide whatever the total is, integer division mind, so that you drop whatever the you sort of discard everything that is past that point, then you can repeat the process with all the rest of the digits. I'm going to do this in Paint. This will be another famous Mr. Moore opens up MS Paint and draws stuff moment. Hopefully this wasn't the bad luck. Maybe this was the bad juju that caused our last lecture to go so terribly, but I'm going to do it anyway. So let's say you have a binary number, right? 0100111101. So so you have this in decimal notation, right? You have this in decimal notation, but underlying that decimal notation, this is what it looks like, right? So basically what you do is, with respect to your first number, in order to get at what this one is, if you just ignore all of this, then you get what that is, right? Now, you find out what that number is by going mod 2, right? Because this is either 0 or 1. It tells us whether the number is even or it's odd, right? So that works, right? That works to extract the value of the least significant byte. Since we know how that operation works, we then can operate the same, we can do the same operation on the rest of the string. We just need to move it down by 1 bit, right? So this is also sometimes referred to as a right shift operation. And in a lot of programming languages, you have a right shift operator. It's two greater than signs. It's like N3 means move N 3 bits to the right. There's a corresponding left shift operator that moves things bits that way, right? And, it sort of depends on what language you use, how the specific semantics of that are worked out. But if you examine this, the rest of it, and you say, okay, I'm going to call this, I'm gonna call this the same. This is the thing I'm operating on now. I can perform the same mod2 operation to then extract the next bit, and then operate on a smaller one, use mod2 to extract that one, smaller one, use mod2, extract that, all the way on down until we have just one left, and, you could just read that one. So, and this, this is getting into some bitwise operation, which is, I don't think actually something that we cover in this course, but bitwise is an extremely useful thing. I have a question comment. I saw something online about using the sign operator for finding even or odd because it looks for the smallest bit. Could it be used instead, and can you explain in short if it's useful? Yes, so it is a bitwise operator. Choop. So, my goodness, I actually don't know. Let me just quickly look up what. No, stop that. Bitwise Python. Let's see how this works. Maybe you have to import something. Oh, okay. So they just work. All right. So let's try it then. So if you have x is some binary number, right? And let's say y is some other binary number. Then you've got some options. The one that you're talking is called bitwise and it doesn't work. All right. Will this work? I wonder. Yeah, sort of. Maybe. Not really. Decimal? No? Okay. So, I'll do some easy ones. So let's do 1111 or 1100 and 1010. So this one is 10, and this one is 14. No, 12. Pardon me. Yeah. So this will be cool. So the bitwise and no. This is a very important. This is very interesting actually. So with bitwise, it basically operates like the Boolean and operator, but as applied to the individual bits that make up a number, right? So if you take a look at these two numbers, the first two numbers are both ones, so if these were Booleans, it'd be true and true. True and true is true, according to Boolean and, so we get 1, 0, 0, 0. if you want the Boolean OR operator, that is the first 3, because either one of them being 1 makes it into a 1 bit in the final representation. What else do we got? Exclusive OR is a fun one. It's not one that you commonly use or see, but it's basically, imagine there's an extra 0 there, right? So it's basically just if you took OR and removed the cases where ANDs were the case, then you'd get exclusive OR. And if you print and as with respect to that, you can do binary representations of shifting operators. So why is it saying, shouldn't that be Y? How did X and Y get mixed up? It's very strange. Y should be... Did I get these confused? I did get them confused. This one is 12. That one is 10. Okay. Good Lord. Okay. So, sorry about that, folks. So, if you notice, if you take this one and you put a 0 there and you remove a 0 from the end, that's the right shift operation. That's the same thing as dividing by 2, just so you know. In fact, you can actually you can perform like a minor tweak on your code whenever you're dividing by 2. If you use a right shift operation instead of doing the division by 2, the right shift operator is actually a heck of a lot more efficient time-wise than the division operator. So you can actually squeeze a little more. You can squeeze some more efficiency out of your algorithm by doing that. But that's like bit whacking optimization, which is way beyond the scope of this course. Oh, okay. Thank you, Mars Lettuce. So you can convert it like so. You have to specify the base. So int 2. Yeah, that works. So there you go. Similarly, there's a left shift operator, which makes things bigger in the same manner. And and there's also the not operator, which performs what you might consider a Boolean negation. So tilde x is just negative. Okay. There you go. That has an interesting interaction with 2's complement representation. Anyway, so that's a rough intro to Bitwise, but that's what you're doing here. So yes, if we wanted to, oh man, I just gave away the answers. So, question. What is the binary base 2 representation of the following base 10 number? Is it 1, 10012, 2, 1001001, 3, 1010001, 4, 101, 0, 1, 0, 1, 001, or 5? I do not know. Please enter your answers into the comments. as it turns out, both 3 and 4 are correct. Remember that just like in decimals, any zeros that are on the front don't actually count. However, sometimes it's actually useful to include leading zeros when you're working in binary representations. So when you're working in binary, it is often the case that the number of bits that you're dealing with is strictly constrained. Like, for example, if you're working in hardware design and you're designing registers, and registers only have a certain number of bits available to them, it's important to know what all of those bits are doing. So it can be useful to explicitly state what all of the bits are. So you will very commonly see people writing in languages other than Python, although it might also work in Python. You'll see binary numbers like this, which have been separated either by spaces or possibly more often by underscores. This is just a way of keeping the data tabulated and formatted in such a way that it's easily readable by human beings. So that's a thing that's often done. And you can see that, like, even though these zeros are technically redundant, they are still put in anyway for the purposes of readability. So if we wish to convert from decimal to binary, let's whip up a quick algorithm to do so. So def dec to bin. And I know I just showed you guys how to do it with a pre-built function, but let's do it anyway. So while d is greater than 0, we'll need a bin. B is going to be our sum. B equals B concatenated with, on the front, the string interpretation of d modulo 2. There you go. And d is integer divided by 2. And when all of that is finished, we shall return b. And we should actually apply something to that and see what we get. I've mucked up my loop somehow. Oh, maybe I should delete this thing. Maybe that would help. Nope. Ha! Wow! There you go. Interesting. Interpretive languages, my friends. You can forget an assignment and it won't complain. Amazing. Yes, thank you. Thank you, Taymor. So, as you can see, we are getting the same binary number that we put in at the top here, which is good because that means that we have written isometric functions. Or not isometric. Complementary functions? The one where one undoes the thing that the other one does. That's what we're doing. Anyway, so there you go. So you can see, I'm going to see if I can finish this section and then we'll take our break. So you can see with respect to this implementation, rather than doing the fancy schmancy conversion to a string directly. They have the literals in there, and they're using an if statement to decide on the evenness or the oddness. You don't necessarily have to do that. My solution is slightly shorter. And that's, it's still using a while loop, though, because there's no obvious data structure that we're iterating over. Inverse function. Thank you very much. Yes. Follow Nick's advice with respect to notification settings. So, yes, and that's what they do in this slide. Wah, wah. Anyway, so, okay, we're going to talk about the other bases when we come back from the break. Stay tuned. So, let me just check to make sure I am! Okay, I've remembered to... I see someone is trying to start a beef between McMaster and Waterloo in the chat. We will not give in to such childish tactics. Obviously, McMaster is better, because it's the one I'm currently at. That's why. Ah! Beat that! Maybe you could get me to admit that Waterloo was better if I was currently going to Waterloo. Did you think about that? Do you all suggest switching from Mac to PC if you're trying to pursue a career in computer sciences? It kind of depends, man. I'm not like I'm not like what you might consider a professional, industry professional, but I'll tell you a couple of things. Number one, if you intend to do any app development whatsoever, you need to have Mac equipment, which I suppose makes a certain degree of sense, but, you know, in some ways it's kind of like you have to buy into the Macosphere in order to be able to make something for an iPhone or something like that. So if what you want to do is Mac development, then it pays to have and know a Mac. The same can be said, but not to the same degree, I think, with Windows stuff. But anyway, generally speaking, if you like, it really depends on what you want to get into. If you want to get in more on like the server side and doing networking type stuff, then I highly recommend learning some Linux, because a lot of the world's servers are done in Linux, so that's a good thing. If you're on a Mac, then Macs are kind of in some ways already similar to Linux. You can do many of the Linuxy type things in a Mac, if you know where to look for them. And this is becoming true with Windows as well. Like Windows has this Linux shell integration thing now, which, you know, is a day late and $1 short if you ask me. But, you know, anyway, it really depends on what type of development you want to do. Algorithms work the same no matter what operating system they're on. Anyway, there's nothing wrong with Linux. Linux is great. Frickin' Linux critics in the chat? Jeez. Anyway, so let's talk about other base systems. Octal exists. You'll probably never use it. It's included in the slides mostly for legacy purposes. It's groups of 3 bits is a good way to think of it. So everything is base 8, hence octal. But yeah, groupings of 3 bits. Hexadecimal is one that you will probably see more frequent even than binary in terms of actual day-to-day programming usage. Hexadecimal digits are groupings of 4 binary digits. They are numbers that go from 0 to 15 in terms of the actual individual digit value. Since we don't have numbers for 10, 11, 12. Like, we do have numbers for them, but they are compound numbers, right? They are composed of more than one digit. So we have single-digit single-digit indicators for the values of 10, 11, 12, 13, and 14, and 15. They are A, B, C, D, E, and F, which is why sometimes if you look at like really old like passwords and stuff, you'll see things that are like mnemonic phrases that are written in using just A, B, C, D, E, and F. I think there's a bit of that in the one of the assignments upcoming as well. But anyway, hexadecimal is really, really useful. So, for example, a hexadecimal number might be FFE6. And in terms of integer, that becomes, if you want to convert it to decimal, doing it the quick way, 65,510. A really quick way to figure out what the maximum value of any number of bits is to just run it through this, right? So this is, each one of these is 4 bits, so this is a 16-bit integer. 16 bits are not uncommon for integers. If you want a 32-bit integer, want to see what the maximum value there is, there you go. A little bit of a side question, but when will assignments 5 and 6 go live on Avenue to Learn? I was under the impression that they already were, but I can double check that. Let's see. Yeah, they look visible to me. You should be able to get them and download them. So, presently, there you go. Yes, all MAC addresses are hexadecimal. So the thing about binary representation is that it takes a very binary. In some ways, binary representation is like old Entish for my Lord of the Rings fans in the crowd today. It is the older language in which it takes a long time to say anything, and you never say anything unless it's worth taking a long time to say. Hexadecimal is the peppy younger brother who can say 4 times the information. He can say the same information in 1/4 the time. So there you go. What's the point of hexadecimal? Well, it's what I just said. If you take a look at binary files, like files in binary representation, you can often, you have what are called hex editors, which represent the binary contents of the file in hexadecimal notation, just because it's easier to work with, and it takes up 1/4 of the amount of space on your screen. But yeah, it's a useful thing. Hexadecimal, especially if you ever get into embedded systems or hardware systems or anything like that. Basically, the lower the level, the closer you are to the CPU and the processor in terms of the work that you're doing, the more likely you are to run into things like bitwise operations and binary representations and hexadecimal representations. Useful stuff. It's also always good to know what your computer... Wow, that really does look terrible. Wow. No, I don't want to save that. Good Lord. It's always useful to know what your computer's actually doing underneath the hood. Yeah. Anyway. So, let's talk about how to represent real numbers, as opposed to all those fake numbers we've been doing up till now. Wah, wah. So anyway. Ooh. So that's a mistake on this slide. I'm just going to make a mistake, a little note that there's a mistake on this slide. Which slide are we on? Slide 18. These should be 10s. So, in decimal representation, when you put a point in, everything past that point is expressed as power multiplied by powers of the base number, but with negative exponents, right? So the same is actually true in binary representation. You've got things ahead of the decimal point, you've got things behind the decimal point, it's just everything is base 2. So, base 2 because it's binary. So this is an interesting thing. This is an interesting thing that leads to some problems, because one of the results of this is that there are actually there are numbers that are representable in the decimal system that are not representable in the binary system without infinitely repeating sequences of digits. Right? Now this is a technical point, and we're going to get into it. So, if we want to represent let's say we want to represent 0.1, right? If we have 3 decimal places in which to do it, you can do 0.001. This will give you 1.25, right? And obviously, if you moved this one more over, then you'd get something less than 0.1. So there's no... Basically, the more digits you add, the closer an approximation you get to the number you want, but you'll never actually hit it. So if you have 5 digits to represent it, you would have 00011. That yields the value 0.09375, which is, again, it's closer than 0.125, but it's not. We're still pretty far away from 0.1. If you have 9 digits to represent it, you can get to 0.099609375, or 51 out of 512. This is closer still, but the problem is that you can't actually achieve it without a infinite series of 2 zeros alternating with 2 ones. This isn't... this should come as no surprise to anybody who's tried to divide 1 by 3 in a calculator, right? 1/3, although arguably a very intuitive number from a sort of, I don't know, evolutionary psychology standpoint, maybe not that particular standpoint, you can see 1/3 is a good handy number to be able to represent, but it has no finite representation within the decimal system. In the same way, 1/3 has no finite representation within the binary system. So, so I have a comment. This is the reason why round 2.5 outputs 2 and round 3.5 outputs 4. Yes, this is the reason, and we're going to get into it. I'm just going to skip ahead and... Yes. I want to copy that to answer your question. Copy. Paste. So let's see what 2.5 is really. Oop, that was a very dramatic enter, and there we go. So 2.5.00000. Well, is this going to be this isn't quite the dramatic reveal that I was hoping for. Because you need to actually invoke the division. Well, is that still not working? Very strange. You ever have a plan in your head and then it just doesn't work out? But 2, 3, 4, 5, 6, 7, 8, 9, 10. There you go. This one works. So, yeah. Dosno? Yeah. Anyway, so this is a point that a lot of people have a lot of confusion with normally. But essentially, It depends on whether you're talking about it depends on like the divisibility of the bases and stuff like that. So here's a question: which of 3/4 and 1/3 have a finite binary representation? Is it A or 1, both, 2, only 3/4, 3, only 1/3, 4, neither, 5? You have no idea. Please answer your enters in the chat now. Oh, dozenal. Right, so a 12-based number system. Yeah, it is quite divisible. That's true. But the reason that the binary system is used in computers is because in the electronics, there were some early experimentations with the idea of analog computers. However, it turned out that you could, if you wanted to miniaturize stuff, we needed solid-state electronics, essentially. Although miniaturization led from solid-state electronics. We didn't invent... Well, anyway. In solid-state electronics, which is essentially the transistor, everything operates on high and low signals, right? So you can have a switch. That's what a transistor is. It's a little tiny piece of silicon that functions as a switch. And switches are either on or they're off. They either have high or low voltage. Excuse me. So for that reason, 0 is low and 1 is high, and that translates directly into electricity, which is why the binary system works in... that's why it's miniaturizable and why it beat out all of the other competing formats for representation. So the 2's have it. 1/3 does not have a finite binary representation. Only 3/4 does. So if we wish to represent stuff in Python, there is a standardized format which is used to represent what are called floating point numbers. Floating point numbers are, of course, the format that's used across all pretty much across every computing device. It is a standard, the International Electrical Engineering something. I forget what IEEE stands for, but they standardized the floating point representation so that there's exactly so many bits in it. So many bits represent this, so many bits represent that, and everybody follows the same standard, so nobody's messing up anybody's digits. So in this format, you've got, well, let's see here. Yeah. Anyway, the part of the floating point number that represents the actual part of the number that is the you know what, I'm going to skip ahead a little bit. We're going to talk about floating point numbers. I'm trying to talk about floating point numbers, so we're just going to go to the slide. So, floating point numbers are consisting of a fractional component and an exponential component. They are essentially the same as scientific notation, right? So in scientific notation, you have some decimal number that is then multiplied by some power of 10. In floating point, you have some fractional number, which is represented by some power of 2. The size of the allowable size of the exponent of the 2 is directly dependent on how many bits are allocated to the exponent, and the size of the fraction that's representable is directly dependent on how many bits are allocated to the fractional component. So, you know, to 1.00101101110110, etc., times 2 to whatever power. So we have decided as a species that the fraction shall contain 52 bits in normalized form, that is to say, with a 1 leading before the point, and with a leading 1 before the point, and with the exponent having 11 bits. This gives us an effective range of from negative 1022 to 1023. So that has certain implications. There is a fixed smallest and largest number which can be represented inside of floating point format. In the case of the smallest number, it is 2.2250, etc., times 10 to the negative 308. So you can kind of think of this in the same way that you would think about the electron charge or the mass of a proton or something. It is the smallest indivisible number that can exist. It's the quanta, and everything else is some multiple of that. So there you go. So these are relatively large numbers, and hopefully we don't run out. That can be a real problem. So anyway, when you print a number, typically the standard output will only give you the first 16 digits of the number, even though the number will continue and trail off from there, right? So, for example, if we have some like weird fraction involving prime numbers, right? So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And you can see that this is like clearly a repeating, this is a non-finite. It would take an infinite number of decimal places to precisely represent 17 out of 27. You can extend the number of digits that you see by using this format function. So you can see that let's put them side by side just to compare though. So you can see that at this point, where it cuts off with a 7, it actually continues. I really want that. It's messing me up. It has to be aligned. I'm sorry. It has to be aligned. Of course it's invalid syntax. Why would it be valid syntax? There we go. Okay, so you can see that this 7 is being rounded from this decimal tail, but you can see also that this repeating pattern breaks down after that point. All right? That's because the underlying binary representation cannot represent 17 out of 27. It's one of those numbers that does not have a finite representation. I think I'm going to just do some more stuff. However, if you wanted something like 1/64th, for example, you can see that this does in fact have an exact representation, and it's because, of course, the number is a multiple, or it's the denominator here is something base 2. So there you go. I'm just going to turn the light on. It's getting kind of dark in here. So yes. So if any of you remember that demonstration that I did with the 10 1/10ths at the beginning of the semester, you can now see why that doesn't work, right? It's because each one of these things is just slightly not the thing that it says it is, right? And that's... Oh, question, what does 0.60f mean? It means show me in decimal notation 60 decimal places and format it as a floating point number. So it's just an instruction to format. You'll find it kind of common with some Python functions that they'll take arguments as strings rather than like enum types as a lot of other languages will do. I'm not sure why they do this, but when we get into file IO, whether you're reading or writing is indicated inside of a string as well. So wait, isn't 17 out of 27 finite because within 60 decimal places the last few were 0? Well, the thing is, okay, let me pull that one back up. So in order for it to be represented accurately in decimal, you would need this to repeat forever, right? 629, 629, 629, etc., etc., etc. What these trailing zeros mean is that we've literally just run out of floating point fractional component to be able to represent it. These digits are smaller than our floating point representation can allow us to represent. This is the limit of how small a number can be. But anyway, the take-home message here is that when you're working with floating point numbers, you can never, ever, ever, for never, ever assume that they have exact values. So many bugs in so many programs caused by floating point problems. So whenever you're testing code using floating point, always use some sort of rounding function if you want to do equality testing. Better yet, don't use equality testing. We're going to get into some slides that discuss safe ways to use floating point numbers. But just keep in mind that floating point numbers are shifty, and you can't trust them. You can't trust them that far. So anyway, yes, on this very slide, in fact. So whenever you're trying to compare floating point numbers, one approach is to just use a round. right? So if you round this to 4 decimal places, for example, it will round it to 4 decimal places. However, you'll notice that if you open up the fractional component, you're still dealing with all of this garbage, right? So if you want something exact, you have to round it to whole numbers, right? But you can, like, most of the time, if you're doing equality comparisons, if you round both things, it'll round it to the same, you know, it both will have the same tail here, so it'll work out. But the other thing, perhaps the more scientific way of going about it, is if you have two numbers, let's say x is equal to this, and I don't know, y is equal to 34 divided by 54. Let's see, does this work? Yes, it does. Drat. Okay, what does it work with the slides? So, if this one is 1/3 3 times, and that one is 1/6 6 times, in theory, yeah, in theory these are the same number, right? But in practice, you get a false if you attempt equality on them, right? Okay, I've got a question. If this is the smallest, if the previous was the smallest number that can be represented, like, why did I say that what was even my claim? Let me do this again. So this here, this isn't the smallest number that like this down here. These aren't the smallest digits that can be represented on an objective scale. Like, if you imagine the number line, right? And, obviously, if you have, you know, 0.1 times 10 to the negative 308 or whatever it is, that's the smallest number. But you also have to consider what, like, maybe it's better to think of it as the amount of precision that you can hold. Pardon me, that's probably a better way of saying it. So, floating point representation cannot hold any precision past this point because it lacks the binary digits necessary in order to do so. That's a much better explanation. Thank you, Mars Lettuce, for challenging me on my gobbledygook. So, past here, you can't record anything. You run out of binary digits. So this is as precise a number as it is possible to represent. So hopefully that answers your question. And hopefully I've demonstrated that you can't trust equality comparisons on floating point numbers. A thing that you can do is you can subtract one from the other and see if that is smaller than the absolute value of some, or you want to take the absolute value of that side, actually. So absolute value is a thing, well, no, they have that in math. Good Lord. It means if it's negative, it becomes positive. So for anybody who's not super mathy geeky who might be taking this course, so if you have some epsilon, right, that can be a pretty small number, and that'll still come out true, right? Because as long as this isn't smaller than as long as that isn't past the point where the representation becomes bad, right, then this works. But to the extent that the representation is still good, come on, there you go. Let's see how many digits we can hold, and this still be the case. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And we'll count 16. So, like, past this point, things start to get wibbly wobbly. But until this, like, as long as you're within a certain threshold, the numbers will be represented accurately to within that number of decimal places. So as long as your epsilon is inside that threshold, then you can use it to determine whether or not x and y are approximately equivalent. So that's the thing to note when you're using floating point representation. You should never think of exact equality. You should think of close enough equality. Approximate equality. That's the word that I was looking for. So I already talked about that slide. Good. So most computers follow the IEEE standard. Floating point computations will have the same results across computers. This is good. Several formats exist, with 8 bytes being the most common. So I had there it is. So there is this is a visual representation of the way that the bytes are assigned to the various parts. So you've got a 1-bit sign indicating positivity or negativity. You've got 11 bits of the exponent and 52 bits of the fraction. The number of bits in the fraction limits the precision, and the number of bits in the exponent limits the range. So obviously, if we took some bits out of the fraction and put it in the exponent, we would be able to represent larger or smaller powers of 2, which would add to our effective range. And if we took some bits out of the exponent and added it to the fraction, then we would be able to represent more precise numbers. So it was, a grand convention of the graybeards was held, and it was determined without equivocation that the correct trade-off between the exponent and the fraction is 11 to 52. Incidentally, over the break, I found my copy of Gulliver's Travels in which I read that, and I just wanted to show you because there's actually an illustration of little versus big endian, and I just thought that might be interesting for you folks. So this is the little versus big endian controversy, which is referred to by the emperor of the Lilliputians as the little endian heresy. Anyway, so another interesting result of this is that you can actually lose numbers inside of large numbers. So if you have something sufficiently large, like one big number like that, and then you add 1 to it, as long as it's a floating point number, that's how you change an integer to a floating point number, integer literal to a floating point literal, by the way, is you'd put 0.0 at the end of it. You can see that the 1 is lost. However, if you delete a few of these digits, it's it's still there, right? There is a certain number after which the 1 gets eaten up, and that's it. So there you go. Now, it might be that this 1 is inconsequential as compared to this gigantic number, but you are still losing information. So just keep that in mind, that this is a thing that happens with floating point. And the same thing happens generally speaking. I think that it prefers large numbers to small. So if we do something like this, plus 1.0 times 10 to the negative 17. Yeah, so it'll consume the small number inside of the big number. So there you go. So if floating point is so terrible, then why do we use it? And that's basically for the same reason that we use QWERTY keyboards. Although over the course of the history of the development of computation as a science, there have been specific circuits that have been designed in order to accelerate floating point operations specifically, because typically within the historical context of computing, floating point operations are highly CPU intensive. They take a lot of memory, and they take a lot of sub operations in order to execute correctly. So lots and lots and lots of things. I think they started this a very long time ago. Processors have floating point accelerators, which make floating point operations go faster, but they only work on things in floating point format, obviously, so that kind of locks us into floating point numbers as a representation. They're imperfect, but they were the best that they could come up with in the 70s or whenever they made that. 60s, maybe? Did it say the date? I don't know. At any rate, we're kind of locked in now. But in Python, you have some alternatives. If you want, you've got decimal, the decimal library, and you've got the fraction library. So if you wish to, if it really bothers you that your numbers aren't being represented accurately, and it should, what you can do is you can use the decimal library in order to represent numbers being held, keeping the same type of precision that you would be by hand. So 28 fractional digits are kept, and the precision can be changed. So from decimal, import decimal. The only trick with decimal is that you have to input the value as a string, right? Because if you don't, this 0.1, which is already a float, that is when it's converted to a decimal like that, it's just whatever, it keeps whatever imprecision is existing in it, right? So yeah, which is the same thing you would get if you had 0.1, possibly, although again the extraneous bits are cut off. However, now it's being encapsulated inside of the decimal type. So the point of decimal is that it overloads a bunch of these operators in order to make it work the way that you should expect it to. So for example, if we do that thing that we did above, if we have this plus that, you can see that it's still holding all that precision. Regardless, like this is something that would have been eaten up. Oh, I see it's only displaying so much, but it's telling you there's something back there. It's not getting eaten up by the operation in the same way that a floating point number would. So, I have a question. When you import a library in something like Python, does it already exist on your computer and you just load it into memory, or do you download it at this time of use? Generally speaking, for most programming languages, you're in situation A rather than situation B. Lots of stuff that you, like generally speaking, you have to install the library before you can use the library. The import statement uses the library. Installing the library would be something you'd have to do like by, installing Anaconda or using pip in Python. Many programming languages have what are called package managers, which manage packages of libraries for use. However, in this context, the decimal library was installed on my computer when I installed the Anaconda distribution. It might even be included in the Python base package. I wouldn't be surprised. So I'm just loading it to answer your question in a far less verbose manner. So that's the decimal library. You may notice that you can do things that you can't do in. So if you print 0.1 plus 0.2 equals 0.3, that's false. But if you do 0.1 plus decimal 0.2 equals decimal 0.3, well, that would explain that. Yep, there you go. So it works. So that's a useful thing. So the issue then that you get into, why don't we just use this all the time, is that it is very, very slow in comparison to floating point operations. Now, floating point kind of has an unfair advantage because it has all that hardware acceleration, but let's see if this works. So let's say we wanted to divide this by 7. I don't believe you. I don't believe you that it was 0 nanoseconds. Wall time. Well, that just doesn't demonstrate what I wanted it to demonstrate at all. Usage error. Very strange. Anyway, that's not working at the moment. Maybe it would work on JHub 2. I'm not sure. By the way, you don't have to worry about magic functions. There's a little bit about that in the Jupyter Superpowers notebook, which I think is up on JHub 2. It's got some interesting things like how to enable the debugger. But anyway, so if you want to, let's just go over fractional representation now quite quick. So if you would rather not have all of your fractions evaluated, then you can actually represent rational numbers in a manner which preserves both the numerator and the denominator. So this is the fraction representation. So fraction 1, fraction 3, if you divide them, you get fraction 1, 3. So there you go. So here is your great big cheat sheet about what you should do about the fact that floating point is somewhat unreliable. Number 1, use integers instead rather than using floating point numbers. For example, if you are trying to compute a dollar value, calculate it in cents so that there are no fractional dollars. Compute in millimeters rather than meters. All of this keeps all of the numbers above. It keeps you out of decimal range, which allows you to avoid using floats. Use the decimal or fraction standard libraries instead. Oh, so standard libraries, so they'll come in the standard distribution. They are slower, but more reliable. Use a library for interval arithmetic with float. This gives safe lower and upper bounds, although it takes twice as much memory and time. Or use a problem-specific library or check literature for algorithms with known numerical properties. For example, if you're trying to solve differential equations, use symbolic computation, as in computer algebra systems, instead of a programming language. That's maybe not at all good advice. And 6, when using float, never compare equality. Check results within a tolerance. That is good advice. There we go. So there we go. That is our second topic. So we will reconvene at 7:30. See you folks in a few minutes. Hello, folks. I just wanted to show you my kitten again. Hello. Yep. This is your third time on stream, I think. You just keep getting captured and shown to people. What do you have to say to the internet? But, like, look how floofy her tail is getting. It's amazing. Look at the tail floof. Come on. There. Yeah. You're such a squirmy kitty. Yeah. Anyway. There we go. Well, it's always like things are pretty terrible right now, like objectively speaking. So we need to find whatever like happiness we can in the world, and if it's something like if something as simple as looking at a picture or a video of a kitten can bring you happiness, then isn't that worth something, Anyway, enough philosophy of cats. So, let's talk approximation algorithms. So, you guys might remember this particular problem back from the first set of slides. Oh, no, 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 no. What? What? No, no. No. Oh, hey. Zip. Ha! I'm terribly sorry. I don't know how that happened, but my volume slider for my microphone channel was all the way down here. Anyway. The mic is not broken. Anyway, so if you guys remember our if you remember this problem from the first slide set, we were trying to find the x-intersect of a monotonically of a function that's monotonically increasing on some interval from a to b, right? Just to remind you what our approach to this algorithm was, we calculate some midpoint, the midpoint between a and b, check whether f at m is above or below x, and then if it's below, then we know our intersect has to be on the b side, and if it's above, then we know it has to be on the a side, generally speaking. So, let's revisit a question. Hello. Spoop. Gotcha again. So let's revisit a question. If we, in the previous version, we knew we were finished when our x-intersect was within a within a certain epsilon of, well, if the interval was smaller than some epsilon, then we said that was good enough. So, question, can we take the exact x-intersect by taking the epsilon as 0? And the answer is no. And we now know why. Because we would be dealing with floating point functions. And if we were dealing with floating point values, and since there is some smallest floating point value, right? If the epsilon is 0, like you're always going to have, basically the problem becomes, when in this step, when you calculate m by adding a and b and then dividing by 2, if you are at the level of the quantum, the smallest possible floating point value, any value that you get for m is going to be either equal to a or equal to b, and it will do so consistently, right? So in that manner, you know, and since the x-intersect is between a and b, if m is always equal to a, then obviously it's always the f at m is going to be lower, and if it's always equal to b, then f at m is always going to be higher, and you'll just get stuck in an infinite loop. Right now, the cat is trying to decide whether the crack that I left the door open is large enough for her to be able to open the door. But all of her food and her litter box and everything are on this side of the door, though, so she's technically okay to be in here forever. Oh, is she going to open the door? Nope, decided not to. Oh my god. You know Martin, the bigger cat I showed you? He actually opens doors, like, like a closed door, he will reach up, grab the handle, and open a door. It's the craziest thing. And it was causing us a lot of problems at a certain point in his development until we learned to deal with the fact that he can just get into any room in the house anytime he wants unless the door is locked. Or unless it has a doorknob. Because we got the lever style handles. Anyway, so we need to get through this. So in Python, functions can be passed as arguments. So let's create a generic x-intersect function so that we can do this. And of course, I lose all my indentation. Lose all my indentation. There we go. No problems. There we go. So let's define a few let's have some functions which we're going to try to test for the x-intercept of. We will call them f1 and f2. The most original names oh, hello. Oh, my goodness, she just jumped onto my lap. Hi! You're on my lap. Hop. There we go. You can be on my shoulder. That's an okay place for a kitten. So, f1 and f2, there we go. Just regular, and if you examine these functions at all, you'll see that the x-intercept of this one will be 2, and this one will be some decimal. Boop. She's so cute. So, let's try some tests. Don't drink my water! Go! She drank my water. So, anyway. So the interval that we find for this one, because look, see it's returning the interval, right? Is 0.50. Why isn't it still executing? That's interesting. Oh. There we go. Got my indentation wrong. Thank you. So there you go. Our interval is our x-intercept is somewhere between these two values. This is true because we know that it's 2. But let's see what happens if we enter. Actually, you know what? We're gonna show what what it's doing. So let me just format up a quick string so that it looks nice. And if you think I was quick at that, that's because like literally 90% of what I actually do on my thesis is formatting strings. Invalid syntax. It's because I forgot the concatenation operator. There we go. And it requires an argument. Of course it does. So there, you can see what's going on, right? With the intervals. So there you go. Yes, thank you. My goodness. And now she's just kind of going to sleep. Yeah. She was until I started making all that noise anyway. So, anywho, you kind of get the idea. If we do a different one, we get a different interval because it'll have a different intercept. But notice it's actually pretty precise, right? It goes to, was that 7 decimal places? Not bad. Pretty good for an approximation algorithm. There. So, we can also do the approximate linear square root. So, we can make a linear approximation of square root. Square root is actually a thing that's reasonably like it takes time to calculate a square root, right? So, for this algorithm, basically what we're doing is we're starting at 1 and we're counting up, or we're starting at 0, counting up, and when we go until the square of a plus 1 is greater than n. So in this case, the square of 5 is greater than 27, or the square of 6 is greater than 27. So we know that the square root of 27 is somewhere between 5 and 6. And it will, in this particular case, it'll just give you the lower value rather than give you the interval. So there you go. So for n is greater than 0, how often is b executed? Is it n times, n plus 1 times, the square root of n times, n squared times, or n plus 1 squared times? You can enter your answers into chat presently. That's right. The answer is the square root of n times 3. So this is b is executed exactly as many times as whatever the output of the function is. So if it outputs 3, it's executing 3 times. If it outputs 3,972, then it pardon me, required 3,972 executions to get there. So how about binary search? So remember our binary search algorithm from earlier on, right? From, I think, the last slide set? What we want to do, think about the where the square root is as a search space, right? So we want to subdivide that search space accordingly in order to zero in closer and closer on what the actual value will be. So if we repeatedly replace either a or b by a plus b integer divide by 2 such that the above holds, that is, a is less than b and greater than 0, and a squared is less than n is less than b squared. Then a is the approximate square root. So for 27, if we have a at 0 and b at 8, a is 0, b 8. So if what would the evaluation would be if c times c is less than n, then we set a equal to c. So c times c is 16 in this case, c being the midpoint, right? So that is less than, so it gets applied to a. The midpoint should be 6, so 6 is greater than, so it gets applied to b, and then 5 is the midpoint, so that gets applied to a, and then we're done because we've narrowed down the interval suitably. So, in this particular example, for a, we'll take 0. For b, we'll take the smallest value satisfying a 0 is less than a is less than b, which is 1, and we multiply it by 2 until it satisfies a squared is less than or equal to n is less than b squared. So you can do that. You might also say, we know from the numerical properties of square roots that a square, like the square root of a number is at most that number, right? So you could, in theory, just do something like n plus 1 or something like that. But, pardon me, that's neither here nor there. So how often are these loop bodies executed? The question is, when we go to the binary search for integer square root, how much time are we actually saving? And in the same way as the previous binary search that we did in a list of integers for a specific integer, we're actually managing, is it supposed to be b squared? Let's see, b2, where is b2? Hup. Oh, yeah. Yeah, that's supposed to be a squared. All right, that is 2 strikes, Mr. TA, who updated the slides. Yes, it's meant to be b squared. So our algorithm here becomes logarithmic rather than linear, which is good. Logarithms are good. So the first loop sets b equal to 2k greater than n, the square root of n, after k executions. The second loop halves the interval b minus a at every execution until a plus 1 equals b. Hence, also takes k executions. Hence, the loop takes k log 2b, right? So this is a logarithmic relation. So we have k approximately equaling log 2 of the root of n. So we've improved how fast things run by making it into a logarithmic function on what it was originally, which is a good improvement. Generally speaking, like, that's a paper. If you can make that, if you can do that originally, that's a paper. And I realize I'm going through these reasonably quickly, but time runs short, as it usually does on this particular set of slides. So, Pythagorean triples. Let's try to make this one more efficient too. So, a Pythagorean triple is a set of integers that, a set of whole numbers that make a Pythagorean triangle. If you wanted to calculate all of these, the simplest way is to do it by brute force. That is to say, enumerate all of the values of a, b, and see if they form a Pythagorean triple. So you can see we've got, for some range n, right, you want to specify how many, how big a triangle you want to check for. And it's just a, b, and c. We're for looping over the range from 1 to n plus 1 of each of these. And then if a squared plus b squared is equal to c squared, then you print the triple. Very simple. So, for n is greater than 0, how often is a executed? Well, a being this line here. Well, this is how nested loops work. You have to multiply each of the number of executions together, right? Because the for loop, the innermost for loop, will execute in its totality once for every execution of the b for loop. The b for loop will execute in its totality once for every execution of the a loop. So it's n times n times n, which is n cubed. And cubed is not great. I just explained all that. So, rather than going over all of the values of c, we can calculate c from b and a and then check if it's an integer, right? So, rather than enumerating all of the possible c values that might exist, what you can do is you can just, you can derive it using the Pythagorean formula. And so long as that comes out to a whole number, then obviously it's a Pythagorean triple. This eliminates, and I realize these are all quizzes, but again, I need to move through this. Because we're now dealing with only 2 loops here, we're no longer dealing with an n cubed algorithm. We are dealing with an n squared algorithm, because we have n executions of the a loop and n executions of the b loop. And that you multiply them together, and that's n squared. What does enumerate mean? It just means list in order. So, it's a good question, actually. Mention a number of things one by one. There you go. Or formally, to establish the number of. So there you go. Originally from the Latin. And it has been decreasing in use over time. Anyway. Which is probably why you didn't know what it meant. So, yes. So this is good. This is savings. So, next we decide Well, if we print 3, 4, 5, which is the quintessential Pythagorean triple, and we print 4, 5, 4, 3, 5, is this really necessary? Is it necessary to have all of these repeated triples? By the way, this is a one-liner in Haskell. You can restrict it so that B is always greater than or equal to A. And if you do that, then you eliminate all of these redundant cases. So you have replaced the 1 in the range with A, which is clever. So in comparison to the previous version, you're actually only executing the decision statement in the middle half as often, right? Because on average, if you sort of, the further you go up the range of A, the fewer cases there will be to check in the B loop, right? And you'll start off with when A is 1, you're checking all of the B range, and when A is n, or n minus 1, then B can only also be n minus 1, so you're only checking 1. So in the same way that, like, on dice, when you roll, like, a 3-3, it's a 6, and a 2-4, it's still a 6, and a 1-5, it's still a 6, etc., etc. In that way, you end up with only half of the number of executions actually occurring. It's not quite the same as eliminating the loop completely. It's still proportional to n cubed, or sorry, n squared, but this is still an improvement. So if we know how many steps a program takes, depending on the input, we can use this to predict the execution time. This can be done without knowing the details of the processor and the compilation to machine language, because it's based on the structure of the algorithm. So you'll notice we've got linear time, proportional to n. We've got n logs log n. Generally speaking, when a computer scientist says log, they mean log base 2. N squared, n cubed, n square root of n, log base 2 of n, and there's one that is especially nasty, which is not listed here, and that is 2 to the n, which is stuff like the NP hard problems that we were talking about when we talked about the coin example, the make change example. For those of you who are going on in computer science after this, this is the concept of, this is like your rough introduction to the concept of big O notation and algorithmic complexity. So we can actually classify algorithms according to which one of these functions it follows. So there you go. So, question, suppose it takes t seconds for n equals 200. How many seconds should it take for n equals 400? Well, given that this is the triple nested loop, yes, we have to move through this, sorry. It's 5. It's t cubed. So, each of A, B, and C take different n values in all combinations, so A is executed n cubed combinations in reality. For n equals 200, 200 cubed executions of A occur. For n equals 400, 400 cubed executions of A occur. So, oh, pardon me, I got it wrong. Haha, it's actually this one, T8. Good lord. So, because basically the number of executions has doubled, the amount of time it takes is multiplied by a factor of 8, because it's proportional to n cubed, but it's not cubing the execution time itself. Right. There you go. So, suppose it takes t seconds for this one, where n is equal to 200. How many seconds should it take for n equals to 400? Well, this is the 2-loop version, so we're operating with an n squared algorithm. Our proportion between n and between the first n and the second n is again a proportion of 2. So our answer will be 4t, by the same reasoning as the previous one. And let's suppose for this one, it takes n equals 200. How many seconds should it take for... it takes t seconds for n equals 200. How many seconds should it take for n equals 400? And this one, I'm actually going to wait for you guys to respond. Is it 1, 2t, 4, 2, 4t, 3, 8t, 4, t squared, or 5, t cubed? What a cutie. So we've got people answering variously. 4t, which is answer 2. 1, 2, 4, 1, 1, 1, 2, 2t. So, bear in mind that this is the version which we have B executing starting at A. So we already established previously that when you do that, you're actually, it's still proportional to n squared, but you then divide by 2, right? So, for this one, if you have the proportionality, right? The ratio, is it 200 to 400? 400 to 800. So it's still the same proportionality, right? So it's essentially the division by 2 cancels out, right? Because both of these are running with that divide by 2 included in there, right? So the proportionality between 200 and 400 is still going to be 4, despite the fact that this this algorithm runs in half the time as this one, right? Because what we're interested in here is not the absolute execution time, but the relative execution time, right? N equals 200 relative to n equals 400. So there you go. Answer number 2. So, now for some cautionary tales about floating point numbers. So, Let us consider the quadratic equation. A squared, it's listed above. Let us copy and paste some of this code. Copy. Paste. Then we can execute some stuff. Just to prove it works. There you go. That's the solution. Notice this is in floating point, so we are in dangerous territory. However, if one of the values is very large in comparison to the other values, we get problems. So the thing is that 0 is not actually a solution of this equation, right? So that's a problem, right? You can't, because you got the +1 here, if you put 0 in for this x and that x, you're not going to get, you're going to get a 0 equals 1, and that means, you know, if 0 equals 1, then fish equals banana. It can be proven. Actually, like technically speaking, in terms of formal logic, if you can prove that false is equal to true, then you can literally derive any proposition from false equals true. But anyway, so let's see what's actually happening here. We have this b times b minus 4ac step here, right? So during that step, we've got negative 2e8 times negative 2e8. That minus 4 times 1 times 1. So the problem with that is that you get that issue where a floating point will eat up a number that's vastly smaller than it, right? The loss of significant digits. So because that happens, we have this problem where x, the value of the solution, is 0 rather than what it should be. So there are a couple of ways you can avoid this problem. Number one, you can use the decimal library to avoid loss of precision. And you can also use an alternative formula that perhaps is more numerically stable and doesn't lead to large intermediate values. This business of multiplication on large numbers is actually one that comes up. But anyway, so solutions to the quadratic equation are also related by Vietta's formula. Given the solution with the larger absolute value, the smaller can be computed using Vietta, avoiding the loss of significant digits. So, as long as you don't get the 0 first, I suppose. So you can do it that way. That avoids the use of this problematic multiplication. You can look up the reference, but that is actually it. And I guess I didn't need to step through this stuff. I could have waited for you guys to respond. Well, I guess at this point in time, I will open the floor to questions. If you have any questions relating to anything, please put them in the comments now. And I'll see if I can connect my phone to a reliable source of electricity. Could I train the cat to keep the kids off the grass patch? Well, it's actually not an issue anymore. I cut the lawn. I've determined that the grass has had enough time, and so it's now normal grass that people can walk on. It's really just when it's like you're trying to get new grass to establish that that's a problem. So big O notation for the improved Pythagoras is n squared over 2 or 4n. It would be n squared with no over 2, actually. In big O notation, you leave off any constant factors. So with respect to, like, it doesn't matter. Like, the theory behind that is that when you have sufficiently large n's, no constant factor is going to dictate the program's execution speed. And thank you. I like my gamer headphones as well. I am gamer. I game. So with respect to big O notation. So yeah, the constant factor, as n increases, that's going to be lost. That's not going to dictate what the behavior of the algorithm looks like. So generally speaking, in big O, we leave off the constant factor. But yes. Dr. Moore is Anakin, and the kids walking on the grass are the Padawan. Ooh. Ooh. Not the younglings. Did I cut my hair? No. It might just be under my headphones. I don't know. So then why is the execution time 4t and not 2t squared over 2? Because in this particular question, they're asking for what the relative increase in execution time would be, not the absolute execution time. Like, they're not asking how long would it take for 200, how long would it take for 400, right? It's asking what's the ratio between it taking 200 and it taking 400, right? Let me see if I can do paint math. Paint. Don't tell people I like pinball. So, like, if you've got 200, right, and you square that, that's over 400 squared, right? You can, over 2, right? Over 2. This is on the assumption that we've got t is equal to n squared over 2. I'm getting better at this, actually. So that means that's a terrible squiggly arrow. That's better. So that simplifies. Well, is that how that works? So this becomes, 200 squared over 400 squared, right? Which then becomes, 200 over 2 squared over 4 squared. You can get rid of the zeros as well. Is equal to 4 over 16 is equal to 1/4. So I've messed up the cross multiplication anywhere, but the factor that you get out of that is 4, right? the constant, like, it doesn't matter if these were multiplied by 100 million. They would both be multiplied by 100 million, right? Does that make sense? Hopefully that makes some sense. Good. Excellent. Yeah, it's kind of a weird question, but yeah. You have to be conversant in that sort of thing if you want to go into optimization. Anyway, are there any other questions? Well, if nobody else has any questions, then I think that I'm going to be signing off for today. Thank you very much for your time and attention, folks. My goodness. Okay, one more kitten. Meow. Yeah. Choop. There we go. The kitten says, "Good night, folks. I'm very sleepy." Shush, shush, shush. Sleepy kitten says, "Good night." Do you want to say good night? Are you guys picking this up? I hope that was audible. Cool. Anyway. Run along to your tutorials, folks. By which I mean click a different browser window. Good night.